first example for when you include non-integer numerators is 2.5 eighths plus 7 eighths. So first of all, we're going to need to get 2.5 eighths. So how do we do that? Well, here's 1/8, here's 2 eighths, and here's 3 eighths. To get 2.5 eighths, I need to cut this one in half. Let me do that quickly. I would like to quickly note that 2.5 eighths is equal to 2.5 eighths or 2 5/10 eighths. Why is this? 2.5 by itself is equal to 2.5 or 2 5/10 by itself. 2.5 is a mixed fraction. Mixed fractions are written in a certain way where you have an integer and then a simpler fraction right next to it. 2.5 or 2 5/10 is a decimal. Also, I would like to note that 2.5 eighths is equal to 5/2 eighths. If you already know that 2.5, which is a mixed fraction, is equal to 5/2, which is an improper fraction because they're simply the numerator and the denominator, and the fraction is greater than 1. So if you already know that this equation is true, that 2.5 is equal to 5/2, then it would make sense that 2.5 eighths is equal to 5/2 eighths. But anyway, let me do a model to show why 2.5 eighths is equal to 5/2 eighths. First, I'm going to need to cut up 2 pieces of each one representing 1/8 into half. I want to show that 2.5 eighths is equal to 5/2 eighths. Here I have 1/8, 2 eighths, 2.5 eighths. Here's another 2.5 eighths. I got this half of an eighth from the extra of when I created this piece. To show that 2.5 eighths is equal to 5/2 eighths, I will need to cut up these 2 pieces into half. So let's go and do that. So here we have 2.5 eighths. 1/8, 2 eighths, 2.5 eighths. Here we have 5/2 eighths. 1/2 eighth, 2/2 eighths, 3/2 eighths, 4/2 eighths, 5/2 eighths. If I combine these pieces like so, you can see that they look exactly the same, that the first line looks like the second line. Therefore, 2.5 eighths is equal to 5/2 eighths. Because 2.5 eighths is equal to 2.5 eighths and is also equal to 5/2 eighths, that means that we are not only solving in this problem 2.5 eighths plus 7 eighths, we're also solving 2.5 eighths or 2 5/10 eighths plus 7 eighths, and we are also solving 5/2 eighths plus 7 eighths. So back to this problem. We already have now 2.5 eighths, 1/8, 2 eighths, 2.5 eighths. Let's now get 7 eighths. 1/8, 2 eighths, 3 eighths, 4 eighths, 5 eighths, 6 eighths, 7 eighths. To figure out what 2.5 eighths plus 7 eighths is, we can figure out what the total is when we combine them. 1/8, 2 eighths, 2.5 eighths, 3.5 eighths, 4.5 eighths, 5.5 eighths, 6.5 eighths, 7.5 eighths, 8.5 eighths, 9.5 eighths. So 2.5 eighths plus 7/8 is equal to 9 1/2, which is equal to 9.58 or 9 5/10, which is equal to 19/2. If we wanted to, we could have these pieces in a circle. Let's end with the 1/2 because we want to fill up one circle before moving on to the next. So we have in total 1/8, 2/8, 3/8, 4/8, 5/8, 6/8, 7/8, 8/8, 9/8, 9 1/2. First of all, it makes sense for this circle only that we have 8 of these pieces because each piece represents 1/8 of the circle, which means that it takes 8 of them to create a circle. The total number we have of all these pieces is 9 1/2. So that means that 2 1/2 plus 7/8 is equal to 9 1/2, which you may notice is a little bigger than 1 because a complete circle represents 1. Suppose I want to solve this problem without the denominator. How do I do so? Well, first I get 2 1/2, which I have here. Then I get 7, which I have here. And then I figure out what the total would be when I combine them. And the total is 1, 2, 2.5, 3.5, 4.5, 5.5, 6.5, 7.5, 8.5, 9.5. Therefore, 2.5 plus 7 is equal to 9.5. You may have noticed that in the previous problem, it was the exact same as this one, except everything was in eighths. Therefore, to solve that problem, you add the numerators but keep the denominators the same. I would like to show that 2 1/2 plus 7/8 is equal to 2 1/2 plus 7 over 8 without using a model. We do not know that this is true yet. That is what the question mark shows. I've exchanged the 2 1/2 to 5/2. We already know that 2 1/2 is equal to 5/2. However, let me explain without using a model. 2 1/2 is equal to 2 plus 1/2. 2 is also equal to 4/2. Why is that? Well, 4 divided by 2 is equal to 2. So we can know that 2 plus 1/2 is equal to 4/2 plus 1/2. Because we're dealing with numerators and denominators that have positive integers, and we already know for those cases you add fractions like so, that you add the numerators but keep the denominators the same, we can know that 4/2 plus 1/2 is equal to 4 plus 1 over 2, and that would be 5/2. I've also exchanged the last 7 on the right side with 14/2, with 14 over 2. Why can I do that? Well, 7 is equal to 7 over 1. Anything over 1 is equal to that anything because anything divided by 1 is that anything. And that would be equal to 7 times 2 over 1 times 2. I'm multiplying the same number to both the numerator and the denominator, and the fraction would be equal to the original fraction. Why is that? I plan to explain why in a future set of videos, and when I create that set of videos and publish it, I plan to link that in the description of this video. And then that would be equal to 14/2, 14 over 2. Or you can just think that 14/2 is equal to 14 divided by 2, which is equal to 7. So we still do not know that the second line is true. I would now like to simplify 5/2 over 8. Well, 5/2 over 8 is equal to 5/2 over 8 over 1. Why is that? Well, 8 over 1 is equal to 8. Anything divided by 1 is that anything. 5/2 over 8 over 1 is equal to 5/2 divided by 8 over 1. We simply wrote the division problem in a different way. We are now dividing two fractions, and when you divide two fractions, you use the method called keep, change, flip, which I plan to explain why that works in the future set of videos, and when I publish that, I plan to link description in this video. Also, in another, or maybe the same future set of videos, I'll be showing how you multiply fractions and why it works that way. When you multiply two fractions together, you multiply the numerators and you multiply the denominators. And then that would be 5/16. I like to think for this sort of fraction where you have a fraction as a numerator but just an integer as a denominator, as like this. 5/2 over 8 is equal to 5 over 2 times 8, or I'm just simply moving the 2 to the bottom, and that would be 5/16. So I changed the 5/2 over 8 to 5/16. I've also exchanged the 7/8 to 14 over 16. Why can I do that? Well, 7/8 is equal to 7 times 2 over 8 times 2. We're multiplying the same thing to both the numerator and the denominator, and that would mean that the fraction would still be equal to the original fraction, which I plan to explain in a future set of videos, and then that would be equal to 14 over 16. On the right side, I added two fractions together. Why could I do that? Well, these two fractions had positive integer numerators and denominators. I already know that if I add two fractions like in that case where the numerator and the denominator are positive integers, I add it like so. I add the numerators but keep the denominators the same. Therefore, I can note that 5/2 plus 14/2 is equal to 5 plus 14 over 2. We still do not know that this is true yet, but we can also know that 5 plus 14 over 2 over 8 is equal to 5 plus 14 over 2 times 8, which is equal to 5 plus 14 over 16. And now I do know that this equation is true, because the fractions we are adding are simply having numerators and denominators that are positive integers. And we already know for that case, you add fractions like so. You add the numerators, but keep the denominators the same. Because we know the last line is true, we know the third line is true. We then know the second line is true. And lastly, we know the first line is true. So now we know that 2 1/2 eighths plus 7/8 is equal to 2 1/2 plus 7 over 8, which is equal to 9 1/2 over 8. The next video in the set of videos is part 6b, which is the second example of when you include non-integer numerators. If you would like to skip the next examples for this case of non-integer numerators, part 7a is the first example for non-integer denominators, if you would like to click on that.